excuse me, a research physicist, an astrophysicist from the University of California, San Diego at the Scripps Institute. And today is going to be talking about the role of the sun in climate change and related topics. So thanks very much for coming, Dan.
Thank you, Dr. Hendricks. Thank you for coming. I'm going to talk about a topic that for me has just been a lot of fun. I think we scientists are the luckiest people in the world that we just get to do something for a living that's just a lot of fun. I didn't begin my career 25 years ago as any kind of save the world person. I just had an opportunity to do graduate work in Antarctica and thought that was cool, and I never looked back. But climate science, of course, has a bearing on society. Climate change, as you know, has enormous social relevance. And there's, we've come into our share of disinformation and confusion and with respect to the public and perception. And the sun is a big part of this. I'm going to describe this afternoon how the sun governs our climate system, how the sun has been changing over historical time, over the past few hundred years, and what's really going on with the sun, and what's been going on with climate change. And one of the biggest things you hear among these so-called skeptics is that the sun is responsible for all our climate change. We don't need to worry about what we're doing with the atmosphere. I'll get into the details about how that comes about, or how that has come about, but it's just not true. The sun has not been responsible for the warming of the climate and the related changes in our weather systems we've seen over the past century, but yet it is something we need to be concerned about because the sun's output might change later this century. So it remains a compelling research topic. So the title of my talk just comes from a quote from Mark Twain, "Truth is stranger than fiction." The full quote is, because fiction is obliged to stick to possibilities, truth isn't. There's been a lot of fiction put out there about what the sun's role is in the climate system, but the truth is actually a little more bizarre than that. So, for example, what you'll see in the next 40 minutes or so, all kinds of amazing things. You'll see a vast, complex, and chaotic magnetohydrodynamic system that remains stable and predictable for 100 years to within 0.1%. That's how our sun has behaved over the past century. We'll see an example of a conquering army marching across a frozen sea. We'll see a really, really bad nature paper. Papers in nature are not supposed to be bad. And then we'll see actual examples of regional climate warming if the sun were to go dim. And I'll try to explain all of that. Of course, I have 60 slides with me, all of which take 2 or 3 minutes, and the door will be locked. Only kidding. I may fast forward through a few of these things just because I know many of you have to get back to work. But these things, when you get into what the sun is really doing with the Earth's climate, some of the most creative sci-fi writers couldn't make up some of this stuff. So let's just start with some basics about the Earth's energy balance, the energy budget that keeps our planet habitable. The flux of radiation coming from the sun at the top of the atmosphere is 1,367 watts per square meter, averaged over the course of a day and over all of our latitudes. That's about 342 watts per square meter. That impinges on the atmosphere. Some of that sunlight is absorbed by atmospheric trace gases like carbon dioxide, water vapor, ozone. A lot of it reaches the surface where it heats the surface. Some of it is reflected from the surface. Some of it is reflected and absorbed by clouds. And then, so with all that energy imparted to the Earth radiates energy back at infrared wavelengths, and some of that radiation makes it all the way out to space, depending on its wavelength. Some of it is trapped by the atmosphere, some of it is trapped by clouds and radiated back to the Earth's surface. And in addition to all that, we have the latent heat release evolving changes of phase of water. And all of this basically is what keeps our planet habitable. If we didn't have the atmospheric gas trapping, this so-called greenhouse effect, primarily by carbon dioxide and water vapor, our planet's average temperature would be about minus 18 Fahrenheit instead of the 47 Fahrenheit it is on the global average. So the greenhouse effect keeps us alive, keeps our planet habitable. But the thing to keep in mind is that our advanced civilization has evolved and is adapted to a very, very narrow range in climate. The phrase you often hear, saving the planet, is not quite accurate. If the climate were to warm by 10 degrees, life on the planet would go on in some form. We might have 60-foot crocodiles in Wyoming again. But what But we're adapted to, including our agriculture. You know, if you think about what keeps the United States a superpower, we have agriculture that can feed 3 times our own population. We have a temperate climate on a continental scale. We don't have all these tropical diseases that make other parts of the world much less productive and much less healthy. We really have, you know, a huge blessing in terms of our climate, and we're starting to see damage in all of those respects with the anthropogenic global warming. So advanced civilization itself is adapted to a very narrow range in temperature and in weather conditions. We know that human beings survived the Ice Age, but they didn't thrive in the Ice Age. They were just hunter-gatherers. You know. So I've talked about energy balance, but that's only half the picture. And a key point to keep in mind is that as the sun imparts energy to the Earth and the Earth radiates it back, the atmospheric motion rises and falls at various latitude bands. We have rising air at the equator, where the insolation is the greatest, that descends at middle latitudes and then rises again in the polar regions. So you have these cells, what's called a Hadley cell. But then the Earth is rotating under this, so you have an apparent forces that deflect that air motion into westerlies at our latitudes and easterlies or trade winds at more tropical latitudes. And that those bring about our basic weather systems. But as you can imagine, there's friction on top of the ocean and the land surfaces, and then as the winds impart energy to the ocean, they set up circulation patterns. It's quite complicated, and on a small scale, it's very chaotic. That's what we know of as weather. The old saying, climate is what you expect, weather is what you get. Underlying all of this, there's a very delicate balance in the thermal structure of the atmosphere that governs exactly where these weather systems go, where the westerlies will steer. Will they be a little closer to the pole or a little farther away from the pole? Will they become stronger or weaker? Will oscillations such as the El Nino set themselves up in the tropics? All of that is very, very, very fine-tuned toward the temperature structure of the atmosphere. And so it's a very complicated system. It's not just radiation coming in and being trapped by the atmosphere. It's a vast interaction between radiation and dynamics. Just a couple of climate change basics. I'll just go over this very quickly. These are just to emphasize that everything that you've heard about in the news about global warming, it's all been measured. It's not just some back of the envelope theory. It's not just speculation. We know what what our fossil fuel consumption emission rate has been going. We know where it comes from. We know that carbon dioxide has been accumulating in the atmosphere. We know from isotopic ratios that this carbon dioxide accumulating in the atmosphere has come from burning something. The isotope carbon-14 tells us it's from fossil fuels, not more recent emissions of anything. It's all been measured. Not only that, but the actual greenhouse effect in the atmosphere has been measured. NASA has flown instruments specifically for this purpose all the way back since 1970. And since 1970, we've had enough greenhouse gas increase in the atmosphere that we can actually measure the change in radiation trapped by the atmosphere. This is the middle infrared spectrum. This is where all those infrared goggles that you saw in Zero Dark 30. This is the wavelength range they work in. We've actually measured the small change in radiation at the top of the atmosphere that's trapped by this small increase in greenhouse gases that we know we've put in the atmosphere to date. So it's all been measured. There's nothing that's just any kind of speculation. How do you make sense of this complex interaction between radiation dynamics? Well, we have these global climate models, much maligned on Fox News. However, every branch of modern science uses numerical simulation with supercomputers. Everything from astrophysicists simulating the Big Bang to pharmaceutical companies inventing the next drug. Everybody uses supercomputing. It's essential for modern science. Climate science is no different, and what we do is we build a vast physically based simulation of the Earth's climate system in a supercomputer, and these things work very well. Their performance has been almost entirely limited by just the computing horsepower. Back in the 60s and 70s, when people first started building these things, they were only able to simulate the basic atmosphere and ocean. We've coupled them since with sea ice, with aerosols or sulfates, which are our industrial pollution of particles from smokestacks, from automobiles, from burning, from cooking, from deforestation. The aerosols have their own effect on the climate system. They're now simulated in the climate models. Now these things simulate the ice sheet, the upper atmosphere, by geochemical cycling, and it's mostly a function of computers being more and more powerful to handle the physics that we know prevails in the Earth atmosphere system. And they do an excellent job. For a while, we didn't understand why climate model predictions, if you're looking at the lower left figure there, why they didn't exactly track the observed temperature trend. But then when climate models were sophisticated enough to incorporate the sulfates or pollution aerosols in the lower atmosphere, then the model simulations match the observations much more closely. So these things have been tested, they've been validated against past climates, and we know how to use them as predictive tools for the next century. And in particular, if we go back a few centuries, and this is the core of my own research, these things actually do a fairly good job of simulating past ice ages. And I'm going to use the term ice age should be used with caution. I'll get into that in a second. But let's turn back to the sun. Just couple minutes talking about the physics of the sun. So I'm not just throwing jargon at you later. The sun is a gigantic nuclear reaction, a giant fusion reactor, fusing hydrogen into helium, and as this interstellar gas contracts and becomes a star, it will burn the hydrogen into helium for several billion years, depending on its overall size. This vast energy, much of it is trapped within the sun, and it's absorbed in the photosphere. Just as you saw in the atmosphere, there are trace gases absorbing radiation. The same is true in the solar photosphere, where there are all kinds of metals that are absorbing radiation, keeping it out, or keeping it within the sun and letting some of it out. And then beyond that, we have the chromosphere, where the sun is becoming more tenuous. I'm going to use the term main sequence quite a bit. When a star forms, it will start burning its hydrogen, and then there'll be depending on the size of the star, there'll be a very precise relationship between the temperature of the star, which you can observe spectroscopically, and the actual brightness or energy output of the star. And any star that's burning its hydrogen lies on this line called the main sequence. It's just where most stars happen to lie. As a star forms, it joins the main sequence. Once the star begins to burn up most of its hydrogen, the helium begins to burn, and its internal nuclear physics changes. The star will become much larger, much more luminous, and it will become a giant. In the case of our own sun, a larger star will become a supergiant, and then the end point of this is a supernova. The supernova is a very large star that's exploding just because of the unique nuclear physics of its huge mass. The fate of our own star, our own sun, will be it'll spend about 10 billion years on the main sequence, just quietly burning its hydrogen. When that's all gone, it'll become a red giant, and then when the helium is all gone, it will collapse into a white dwarf. So it's important. The thing to take away from this is that on the main sequence is when the star is burning its hydrogen, and then anything that's slightly evolved is not really an analog of the sun. So the sun is also just has a gigantic magnetic field. It's a giant rotating metal, a liquid metal, mostly hydrogen, and as it rotates, it generates a huge magnetic field, which results in sunspots, the mechanism for which I'll describe in a minute. Over the past century, the sunspot cycle has been fairly constant. It goes in 11 years from very few sunspots to a few hundred. The energy output over that 11-year cycle is maybe 0.1% change from max to minimum in the sunspot cycle. And the sun has just been very, very consistent over the past 100 years. Not much has been changing with it. Its energy output has been very constant. At the same time, we know that we're increasing greenhouse gases in the atmosphere. So don't let anyone tell you otherwise. The sun has been constant over the past 100 years. But that is changing. Before the past 100 years, there were a few periods where the sun was noticeably dimmer, and where sunspots in fact vanished. Galileo first described sunspots in the Western world, and shortly after he described them and started observing them, a few other people started observing them, some of the major 17th century scientists. And then, starting around 1645, they all went away for about 45 years. And shown on the upper right here is one of the drawings of a very low sunspot period done by, I think, Hevelius in the mid-1600s. And so we do have some, not quantitative data by modern science, by modern standards, but some good observations of the sun there that are reliable enough to be able to say with confidence that the sunspots did go away. There are all sorts of, of other geological proxies having to do with cosmic ray modulation that tell us that the sunspots did go away and that there was a decrease in magnetic activity of the sun. This is just a little bit more of that. And so what happened in Europe in the 1700s, or the 1600s and early 1700s? Well, the Thames froze over quite regularly, and if you read Samuel Pepys and diarists of that period, they talk about frost fairs on the Thames. Interestingly enough, if you recall your European history, or if you're into historical stuff like the Three Musketeers or whatever, the big bullies and belligerents were up in the north in Scandinavia. We think of Scandinavia as a socialist paradise now. They were behaving like Vikings back in the 1600s. Vikings with wigs and a little bit refined, but they were still behaving like Vikings. And in particular, Sweden was the big bully, and Denmark was trying to hold its own. And they fought a bunch of wars, and they also kind of kept Russia in check. In one of these wars, the Swedish king noticed that a large part of the Baltic Sea was freezing over due to this decrease in solar radiation. He didn't know what was causing it. He just noticed that the water was freezing over, and it was strong enough. He sent his engineers to measure that the ice was thick enough to send his cannons across. So in the middle of winter, he marched his army across and made a surprise attack on Copenhagen in 1658 and won that war, grabbed a lot of land. So I just bring this picture up as climate change has always been a national security issue, not necessarily with freezing these days. There are other issues with warming, but this is our conquering army marching across a frozen sea. They couldn't do this today, obviously, but they could when the sun was driving climate into a cooler period. So just a little bit of mention here on what causes these Maunder minima and what they are. It's basically a shutdown of the sun's magnetic activity. First, to understand it, we have to understand what causes the solar cycle itself. If you think of the sun as a rotating magnet with these field lines that are aligned north and south, what happens over the 11-year solar cycle is that the sun is not rotating constantly at a constant rate. The equator is always rotating faster than the pole, so it's pulling the field lines and twisting them. Twisting these magnetic field lines eventually twists them so much that they begin to break through the surface of the sun and reconnect at the surface of the sun, and we see that as sunspots. For each sunspot, there's a brighter area called a faculum, and the gist of it is that when there are lots of sunspots, there are equally bright facula, so when the sun is magnetically active, it emits a little more radiation than when the sunspots are not there. So at the height of the sunspot cycle, these magnetic field lines are very twisted, very contorted, a lot of energy going on, but eventually the sun, just like our Earth's atmosphere, the sun's outer atmosphere is circulating, and that eventually drags the field lines back into a north-south smooth orientation, and the sunspots disappear. That whole cycle starts again and goes every 11 years. So at the height of the cycle, when there are lots of sunspots, there are also brighter areas corresponding to each sunspot called a faculum, or called faculae, where the sun is emitting more radiation. What happens during the Maunder minimum, I won't go into too much detail, is that the whole cycle will just shut down for about 40 years or so. It's just a very small change in the way the sun's circulation is going on, a perturbation. We're now able to simulate the Maunder minima in models of the sun comparable to global climate models. And we realize it's just something that we don't know when it happens, it just happens. The sun will just shut down its activity for a good 40, 50 years. Eventually, through another perturbation called the alpha effect, the sun will recover from a Maunder minimum. Again, this is just a repeat. There are not only observations of sunspots, but there are geophysical proxy records like beryllium-10, where when the sun's magnetic field is strong, it will keep cosmic rays out of the Earth's atmosphere. When it's weaker, more cosmic rays will get through, creating more beryllium-10 in the natural environment, which we have measured going back way before the Maunder minimum. We measure that in ice cores. An important thing to keep in mind, because this is just a very small perturbation in what's going on with the magnetic field and the dynamics of the sun, it's very difficult to predict. It's not like the sunspot cycle. It's something that will just happen randomly. And I have a couple slides that kind of show that, but I won't go into detail. These Maunder minima have no obvious periodicity. We can't predict when the next one will happen. We can do autocorrelation studies on our own sunspot cycle. Some researchers have done that and have predicted that there's a respectable chance within the next 100 years we may have another Maunder minimum, where the sun would go dim, comparable to what happened in Northern Europe. And that change in radiation is only about 1 to 3 watts per square meter. It's only about a third of the greenhouse gas forcing we've been doing, but yet it would affect the climate, and later on we'll see how. So there's another way to get at this problem. With just looking at the geologic record and looking at the solar cycles, all we can really say is these things don't have an obvious periodicity. We kind of know how frequent they are, but another way to do it, and this is what I'm going to be discussing with my program at Lick Observatory, is to use solar analogs. If we can study a large number of stars out there that are nearby, that are fairly straightforward to measure, that are like the sun, are all same size, same energy output, same mass, same chemical composition, if we can examine their magnetic activity, their output, then we might have a better way of estimating how frequently these occur, when the next thing will occur. This has been done for a while, and these things here are spectra of the sun's photosphere. And one measure we use for the magnetic activity of the sun is what's called the calcium H and K line emission, or core reversal. I mentioned there's the photosphere, and then there's the corona of the sun. When these features you see here in the sun spectrum at 3790 and 3930 angstroms, these are deep absorption features due to calcium. But you notice there's a little bump in the middle of these things. That's when the corona is being heated by magnetic activity from the sun. When the sun is magnetically active, the corona will be heated and it will create these little bumps in the middle of that deep absorption feature. When the sun is not magnetically active, those bumps will disappear. So you can measure that and get an estimate of the sun's magnetic activity from stellar spectra. And that's been done for a long time. Mount Wilson started an excellent program way back in the 60s where they were measuring this magnetic proxy in stellar atmospheres, and they discovered that most stars, like the sun, have cycling, just like our own 11-year solar cycle. But occasionally, they would find a star like the time series on the bottom, which doesn't appear to cycle at all, or appears to be flat. And they postulated that these might be examples of stars in a Maunder minimum. So that's the essence of what I want to try to do here, but I want to try to do it with a larger sample, and as you'll see over the next few minutes, I want to do it properly. But yet the technique is there. Unfortunately, there's been a paper by a couple of well-known astrophysicists who are very good in their own field, but somehow they decided to be climate skeptics or something. They put out a paper which is very frequently cited and still taken seriously, and I'm going to spend about 5 minutes going through this paper just to show you what they're doing wrong. They basically surveyed a sample they claimed of 74 stars like the sun with this calcium H and K technique, and then they came up with a distribution of how many stars were likely to be in this Maunder minimum state. And this is the graph that this bimodal distribution they came up with, claiming that about 30% of stars out there that are like the sun are in this Maunder minimum state, the implication of which would be that our sun is going to be so variable on century timescales that we really don't need to know what we're doing with the atmosphere. Our climate model forecasting over the next century is meaningless because the sun could just do whatever it wants, whenever it wants. And that paper it's still cited, as one of the core astrophysical results. There is nothing wrong with the actual measurements. The actual measurements are fine. They're actually, fundamental astrophysical measurements that are very valuable. But it's their interpretation that I'll show you is not quite on base. For example, just take a closer look at this graph. They're studying 74 stars, but then look at the y-axis. The samples are in the 50 to 100 per bin. So what's going on there? Carl Sagan, when he used to talk about science in the public interest, he would say we all have a built-in baloney meter we can switch on. When you see things that look a little fishy, you should start thinking about what's going on. So we have this graph that has an ordinate that's in the hundreds, describing a sample of 74 stars. What are they really doing? Okay, let's just read their abstract. And doing okay with time. They say, changes in the brightness of the sun may introduce further uncertainties into forecasts of global warming by the greenhouse effect. The sun is known to vary in brightness on a time scale of years by 0.1% in phase with changes in magnetic activity during the solar cycle. Yes, we know that. and variations of up to 0.4% also correlated with surface magnetic activity have been found in stars similar to the Sun. Yes, that's true. To delimit the magnitude of solar luminosity variations on a timescale of centuries, we have looked at the magnetic behavior of a number of solar-type stars over several years. Observed in random phases of their long-term variability, they give a sample of the behavior of a solar-type star over a long period of time. Okay, so they're using kind of data snippets from lots of stars to build one statistical model of a hypothetical star, which may or may not be in a Maunder minimum. We find indirect evidence that these stars undergo brightness changes of more than the 0.1% observed during the last solar cycle, a result that calls into question the assumption of constant sun in calculations using general circulation models for climate forecasting. So they kind of have an agenda even before they start. So let's look exactly what they do with the 74 stars. Now, the good thing about a scientific paper, particularly one that gets published in a top-flight journal, is you have to say what you're doing. You can be very clever in your writing and kind of spin things one way or another, but ultimately somebody's going to read it and realize exactly what you're doing. So let's look at what they're really doing. They have 74 solar-type stars. 13 have been studied monthly since 1966 and nightly since 1980. There are sporadic measurements beginning in 78 for the other 61 stars, and we've included these to improve the statistics. Okay, so they're really only looking at 13 of these things. We calculated averages at 1/10 of a year intervals for each star and treated each average as a snapshot of one brief interval in the long-term behavior of a solar-type star. So their heuristic is kind of use all of these observations as a model of one star. So their unit of chromospheric activity is in a time interval. The distribution does not give equal weight to each star. Of course, each star is a separate physical system, which might be doing what it wants. Not every star is identical. It's heavily biased to only 13 of them. So the needle on your baloney meter should be moving right now. So it gets worse. Concentrating on the 13 stars that make up the bulk of the data, we note that the time series falls into two groups. 4 stars are magnetically flat. These are their Maunder minimum candidates, showing little or no variation of magnetic activity with time, and 9 stars show a range of magnetic activity similar to the solar cycle. The magnetic activity of the 4 flat stars are almost always lower than the activity of the cyclic stars. Okay, so in other words, there are 13 premium stars. Most of their data were observed beginning in 1966. They know a priori that 4 of them are probably inactive. The other 61 stars with their sporadic data are just kind of added to the distribution to provide window dressing. So they're saying, as they can say, that the central limit theorem applies. They have a larger sample. So by now, your baloney meter should be reading off the scale. It's no surprising. It's not a surprise that they're studying 13 stars. They know ahead of time that 14 of them are inactive. That they're going to come up with a number of 13% or 30%. This graph just reflects a kind of a statistical method just kind of ginned up to get the result that they want. If you go back to the original papers where this Mount Wilson data are published, I don't even know why they even settle on 74 stars, because there are hundreds that they observed. This is a huge exercise in cherry picking. Subsequent people who tried to do this, they never came up with this 30%. It was always around 10% when they actually treated things properly by treating each star as a sample, not some time interval that's arbitrary. So the proper way to do this with solar analogs, which what I'm trying to do with Lick Observatory, is to make sure the sample really contains solar-type stars. They couldn't at the time, actually. Weight each star equally, and then use 100-year flood statistics to estimate when the next Maunder minimum might occur. I'm getting a little bit, I want to leave time for questions, so I'll just kind of skip over things. One thing we've had since that paper is a satellite called Hipparcos, which made very precise astrometrical measurements of stellar positions that allows us to determine whether a star is really on the main sequence. And flipping forward to some of the work by a UC Berkeley postdoc, Jason Wright, he actually found when he went through the Mount Wilson sample, most of these stars they were claiming as solar-type stars are actually slightly evolved. They're not on the main sequence, so even if they're magnetically inactive, they're not analogs of the sun. They're just a star in a different stage of evolution. And when you just apply that Hipparcos data that allows us to, since 1993, estimate whether, or ascertain whether a star is on the main sequence, you automatically cut down the number of Maunder minimum Maunder minimum detections, and cut down on the frequency by which a Maunder minimum occurs in nature. And that's just shown here in Jason Wright's graph. I'll skip over some of these things. So what I'm trying to do now is to try to take this to another step using Lick Observatory, primarily their largest telescope, the 3-meter, and an instrument to the Shell spectrograph, the Hamilton, which is even larger than the telescope, as you can see in this in the picture up there. So it's a beautiful instrument, a venerable piece of equipment that figured prominently in the early planet searches. They made some of the first planet detections in the 1990s. This is a beautiful instrument for this problem. And what we're trying to do is, instead of just working with 100 or so stars that have been surveyed by Mount Wilson, we're going for 1,000. I've called this project 1,000 Suns. This telescope is powerful enough that we can observe 20 of them a night on a good night, and over three years, with the time that we can be awarded, we can cover 1,000 suns. Just increase the sample size by a factor of 10. Nearby field stars. I'll just skip through this. We have done some work with 100 or so solar analogs, making sure that the chemical composition of these stars is very close to the sun, and we use what are called isochrones. The basic nuclear physics allows us to model a star's evolution as a function of a star's age. When it begins burning hydrogen, we can calculate, as a function of its temperature, the magnitude, the energy emitted by the star at a given age. And we can use these model results and given photometric measurements of the star to estimate the age of these things. And we find that there is a correlation between magnetic activity and age, as we'd expect. And I'll just quickly summarize these results of this first study. We find that there's essentially a probability of about 40% that by mid-century we might enter another Maunder minimum based on the statistics we have from the smaller sample. But it's just really not that big, not a big enough sample, and it's not treated as well as we'd like to. We'd like to get the spectroscopic data to do more. One measurement we can make with this high-resolution spectrograph, the Hamilton, we can measure lithium abundance. Now, lithium is an interesting element. It's measured in stars for a wide variety of astrophysical properties. Lithium is just entrained in the star when it forms. It's not produced by any nucleosynthesis while a star is burning hydrogen. It's gradually destroyed as the circulation in the photosphere subducts it down into the hydrogen-burning core of the star. And so generally speaking, as the star ages, the lithium should be depleted. This doesn't happen uniformly. It's not a perfect age clock. If a star has planets, those planets are going to introduce gravitational perturbations that will make the lithium burn faster. But generally speaking, lower lithium in a star is a separate indicator of advanced age. And so I've been starting to measure lithium in these stars to provide a second constraint as to whether these stars are Maunder minimum candidates or just very old stars. And here are just some of the results here, where these the B minus V is just color. That's just the color or temperature of the star, and then on the vertical axis is the amount of lithium. What we find is that most stars that are magnetically inactive, might be Maunder minimum candidates, are also low in lithium abundance, which suggests that they're not so much Maunder minimum candidates, they're just very old stars. This is a further constraint that's cutting down on the frequency with which Maunder minimum events might happen in nature. We're only really beginning this kind of work. There have been some excellent observers at Lowell Observatory also working on this problem, and that what they find, they have actually captured in their time series an interesting case where a star might have been in a Maunder minimum state and emerged from it, began cycling again. What I'd like to do is find lots more of these things, and the only way to find lots more of these things is to increase the sample size, which we can do from Lick Observatory with its large telescope, and it also has a wonderful little 1-meter telescope that can do the photometric work. So it's a great facility for this work. But the results from Lowell Observatory, which largely supersede the Mount Wilson work, suggest that you need to both observe it spectroscopically with our big telescope, and you need to measure a long photometric time series. So basically our results from solar analogs are that only 100 stars or so have been monitored to date. Very few actual Maunder minimum analog candidates have been identified. We just need a bigger sample. But we do, with what we have so far, we estimate that there's a 40 to 50% chance of a Maunder minimum by the year 2100. And that's qualitatively consistent with the work on solar cycles themselves. So I'm going to go back for about 5 minutes into climate modeling. As I mentioned, these climate models do a very good job of reproducing past ice ages. But we have to be careful when we talk about ice age or medieval warming or some of these things you may have heard in the news. When we talk about paleoclimate records, they're very geographically biased. There's a lot of climatic data and historical data from Europe, plenty of climatic data from several centuries in North America. Throughout the rest of the world, it's very sparse. So, climate scientists know how to take this into account and know how to describe their work occasionally, but many people take it out of context. This is just a graph showing that with paleoclimate reconstructions, the hockey stick, the so-called man hockey stick, the very pronounced warming of the past century does show up statistically significant. But the thing to keep in mind is this, as I just said, regional specificity dominates paleoclimate research. Terms like Little Ice Age and Medieval Warm Period, they're really only specific to Europe. As we saw earlier, the weather systems are very dynamic. Warming in one region might be balanced out by no warming or cooling in another region. There's just all kinds of wave motion, all kinds of dynamic effects in the atmosphere, such that when you're just talking about one region and a warming in one region, you really have to make sure is that really just specific to the region or is it relevant to the entire hemisphere. So when you hear people talk about, well, our climate change isn't important now because there was this medieval warm period, and there was Greenland is called Greenland because it used to be green, and there were grapes growing in northern Canada in the 1200s. Yeah, that's all true, but that's just that part of the world where the specifics of the atmospheric circulation set up a much warmer condition that's not representative of the entire globe. Somewhere else on Earth it was cooler. And in particular, if you look at all these northern hemisphere tree ring reconstructions that are used to make the global average is on top, but there are plenty of places where there was really no medieval warm period, no little ice age. It just happens, it's all reflective of the dynamics. Well, where we live, it turns out that North America is actually fairly representative of what went on in Europe. Not quite as dramatic, but during the Maunder Minimum, the mid-16 to early 1700s, North America did cool a little bit relative to the long-term mean. So the question is, I'll address in the last 5 minutes, what if a sun were to enter a Maunder Minimum tomorrow? The solar analysis of solar cycles, solar analogs suggest it might happen. I'm trying to do better work myself to see if it might happen. We can use climate models to get a handle on that. And what we do is essentially set up a climate model with pre-industrial greenhouse gases, and we make the sun go dim in the climate model, consistent with what we know may have happened during the Maunder Minimum. And we just see how the climate model responds. And I won't go through this in a huge amount of detail. Let me fast forward to some of the results. What you find is that not only is there a global radiation decrease from the sun, it sets up a change in weather patterns. In particular, it changes what's called the North Atlantic Oscillation, which changes the way westerlies flow in the northern hemisphere and causes regional warming versus regional cooling depending on where you are. One result when we couple our climate model to sea ice, we find that if you look at the Baltic Sea, the Baltic Sea showed an appreciable increase in sea ice concentration consistent with historical observations and consistent with the fact that an army marched across it in 1658. So that's giving us confidence our model is giving us meaningful results. So basically what changes when you make the sun a little dimmer, and this is why a lot of the result is specific to Europe, is you change the North Atlantic Oscillation. It's one of these major modes of variability in the atmosphere. When the NAO is in a positive phase, you have strong low pressure over the northern high latitudes and a shift northward in the jet stream, and that allows warmer and wetter air than normal to make its way over Europe. When you shift the NAO to a negative phase, that reverses. The jet stream makes its way further south. There's weaker low pressures over the high Arctic, and there's this colder air makes its way over to northern Europe. That's probably the bulk of what happened during the Maunder minimum. It shifted, just the change in energy, in structure, shifted just due to the changing energy balance between solar radiation and long-wave radiation, shifted the Arctic Oscillation into a negative index, which allowed Europe to cool, whereas other parts of the world didn't. And we see that in the model results, that the model is consistent with that change in the North Atlantic Oscillation. We can diagnose that. Let me shift to the one I wanted to show you most. On the bottom here is the surface air temperature change if we just consider pre-industrial greenhouse gas concentrations and make the sun dim like it was in the Maunder minimum. We get these regional warmings versus regional coolings. But if we increase greenhouse gases to about 500 parts per million, where that's the most optimistic of our greenhouse gas stabilization scenarios, we find that these regional warmings are actually much larger. And it's just because we're inducing a larger temperature gradient between the troposphere and the stratosphere, spinning up the North Atlantic Oscillation change even more, and resulting in even warmer conditions over Greenland. And of course, Greenland, there's this giant ice sheet on Greenland, which is already showing signs of melting. A Maunder minimum would actually make it worse. It would increase warming over Greenland, increase our sea level rise. It wouldn't cool the planet. So the takeaway from this is that a future Maunder minimum, just because the sun goes a little bit dim, we still have these greenhouse gases there. The Maunder minimum is not going to just shut down global warming. It will make the Earth a little bit cooler, but it's going to change circulation such that we're going to see regional warmings, particularly over Greenland, particularly over Alaska. We see also regional warmings in Southeast Asia that could potentially affect monsoons and other things that are important for humankind to be aware of and adapt to. So this is the Maunder minimum is not some panacea for global warming. In some regions, it'll make it worse. I'll skip that. So that's what we have to look forward to if we in fact see a Maunder minimum. I would like to do some more work with Lick Observatory to see what the actual frequency is and if we can explain these things better. So just to summarize, we're surveying a much larger sample of solar analogs that have hitherto been studied with these high-resolution instruments on the Very Large Telescope at Lick Observatory, providing better estimates of Maunder minimum frequency. And we want to actually, with our accurate chemical retrievals from these spectra, try to get at the physics of what's behind these things, linking magnetic activity to stellar chemical composition. And we also want to do long-term photometry to hopefully detect these things, catch them in action. And the data set at the same time, by gathering 1,000 spectra, will also be useful for the planet hunters and the exoplanet astronomers, especially as a database for stellar chemistry. So this has a little spin-off there, but of course we're concerned mainly with just one planet, the one we all live on, and aren't going to leave in anytime soon. Finally, just as I've alluded to, there's all this denialism out there. After 25 years of doing this kind of research, never wanting to be a kind of save the planet type myself, the kind of advice I give students is along the lines of the following. Scientists are historically poor communicators. We don't get training in it. We should be getting better training in it, but we're in the lab with our equations and our computers, and we don't give that much thought to it. So I tell my students and postdocs, just pick your battles carefully. You're not going to avoid it, but be honest with yourself about your speaking and debating skills. Some people are lucky enough that they did acting in high school or something, or were musicians or used to be on the stage. I was one of them. But it is very difficult to debate these corporate shills who are basically trained in PR. That's all they do. If you're fantasizing about that Thomas Huxley moment where you're going to shoot down on Fox News some climate denier, that ain't going to happen, because these people are just they're good debaters. That's all they do. And rather than pick a battle you may not be able to win, what I tell people is just convey the depth of your own work and your enthusiasm for it. An actual scientist is the real story, and the public understands that we're all specialized. We don't know even a climate scientist is a specialist in one area, doesn't know everything about everything. We all understand that instinctively when we go to one type of doctor for one thing and another type of doctor for another thing. The public understands that, just convey your own enthusiasm. That will make a better, nonverbal communication impact on people than trying to win some stupid debate where the other side is intellectually dishonest. At the same time, I tell people, try to remain politically neutral. Instinctively, many scientists are kind of on the left, which is fine, and you can't avoid discussing these things, but try to make an effort not to put your politics in there. For every time you want to talk about a carbon tax, try to balance it with a market solution that's already been going on, like the growth of solar energy, hybrid cars, or whatever. Just be careful about it. As Charlie Kennel, a director of Scripps, who was a great help in my own career, he said the best politics is good science. I think that's the best advice. Also be able to refer somebody to a good website, because I don't know if you've ever been to a cocktail party and you get one of these climate deniers, they don't shut up. They will just keep, they'll just keep harping on you, and they will not let you go. So if you just go see this website, you can get rid of them. I tell people, just be able to soft shoe out of a difficult situation you were hoping to not get into when you wanted to have a good time. But anyway, this is what I've been doing. I'm having a lot of fun at Lick Observatory. This program we're going to hopefully complete in about 3 years. I think it'll make an important contribution. I'm just about out of time, so maybe I'll stop now and answer any questions. Thank you. Question.